Hi class, welcome to another session on biomaterials. So we have been discussing ceramics. In the previous video, I just gave you an introduction to bioceramics. So now let us move on to nearly inert ceramics or nearly inert bioceramics. So when I say nearly inert, it means that they're almost inert. I mean, it's very hard to say that a ceramic is 100% inert, right? So nearly inert bioceramics have good corrosion resistance and maintain good biocompatibility. I mean, they're very biocompatible. And examples are aluminum oxide, zirconium oxide, single-phase calcium aluminum silicates. All these are nearly inert. They don't react to the body fluid under normal circumstances. Also, they have exceptionally good load-bearing capacity, and therefore they are commonly used for making hip and knee joints as they exhibit good load-bearing properties. Now, other non-structural use, these are structural use like making bone and knee implants. Now, non-structural use can include ventilation tubes, sterilization device, and drug delivery system. So medical grade alumina contains 99.5% aluminum oxide with silica and alkali oxide impurities of less than 0.1%, and these are usually derived from bauxite, which is an aluminum ore. So the naturally occurring single crystalline alumina is also called as ruby or sapphire, was was very commonly used in dental implant. However, now dental implants have started moving more towards resin based composites rather than using single crystalline alumina, so its use has declined, but it was used in dental implants quite commonly. And the strength of alumina depends upon the grain size and the porosity. Of course, if the material is less porous and the grain size are smaller, then it's just like really compactly packed. So that's why its strength would be very high. And these implants are produced by sintering, that is bonding ceramic powder by cold pressing. And this sintering occurs at 1600 to 1700 degrees centigrade. And these materials are widely used for manufacturing load-bearing joint processes. So now again, you've got this is about alumina. So you have zirconia as well, which exhibits good biocompatibility properties, and it's widely used these days to make articulating ball of hip prosthesis. And as zirconia undergoes a large volumetric change during the phase transformation at high temperature, partially stabilized zirconia, or it is called as PSZ, is used for it produces a PSZ, and that is also used for making implants. So PSZ has a dopant, which is usually yttrium oxide or yttria as it is called, and that is used to stabilize the material at high temperature during phase transformation. So this is one of the main use of adding yttrium into zirconium, that is to make it really stable at high temperature phase transformation. Other than zirconium, carbon is also used commonly as a biomaterial. You'd have heard about carbon nanotubes, lightweight prostheses, and etc. So carbon there are four types of carbon that are used for as biomaterials. So you've got pyrolytic carbon, three. You've got the pyrolytic carbon, vapor deposited carbon, and glassy carbon. So pyrolytic is actually very commonly used for making heart implants and orthopedic joint. They have like good strength, and they're like good wear capacity. They don't wear off that easily, and they're very resistant. So they can withstand quite a lot of stress and strain. The durability is very high, but the most important factor is their thromboresistance. So they do not facilitate formation of thrombus. So we did thrombogenicity in the first unit. So thrombogenicity, sorry. So these pyrolytic carbon are really thromboresistant, so they can be used for making vascular implants. Or that is why they're popular for making heart valves, because they don't facilitate thrombosis and they would not you know um, They don't increase the risk of thrombus formation or emboli formation. So I hope you had a very fruitful session learning about nearly inert biomaterials with me. And I shall see you again with more ceramic biomaterials. So in the next video, we shall discuss porous biomaterials. Till then, take care.